Hi, dear student. Welcome back to the continuation of this 14th class. Before we parted, we're discussing about the fact that Ci, that is the set of continuous function over the closed interval AB, endowed with the infinity norm, it's a Banach space. So what we did, we took an arbitrary Cauchy sequence, and the purpose is to show that it converges to a limit that is still in the space. That is, the limit is continuous over the closed interval AB. So what I would do in the meantime is to quickly, I had a class a while ago, is to open the new Okay, so where we stopped last time, I want to share that page with you. I already opened, that was the purpose. So now let me share that page with you where we stopped. So this is where we stopped. We stop here, constructed this function. And what I said is that we can go back to this formula too. We have this definition. So I'm going to rewrite that, right? Equations 2 equation 2 read for epsilon positive fixed we can find a rank n such that for any mn greater than the rank, this implies that absolute value of f of x as fn of x minus fn of x is absolute value is less than epsilon, and this is true for any epsilon in I. That for any epsilon in I can put it here, I can put it there, but right. But now if I, because this is true for any m and n, I can fix one of them. I can fix n, and then I vary my m. Now, if m varies, I can take the limit when m goes to infinity. Now, if I take the limit here when n goes to infinity, we know already that f sum n of x converges. That's what we did here, right? We know that fn of x, when x is fixed, will converge to f of x, right? So if I fix x also, then I take the limit on n, it converges, right? So I will take the limit. So for x fixed, so this is from this is to 2. So I fix x and I take the limit take the limit. In equation 2. So what do we have? We have for n greater than epsilon, than capital N, we have f of x minus fn of x greater than or equal to epsilon. Now we have equal less than or equal because of the limit. Because we are taking the limit when n goes to infinity. We have less than or equal right here. So what does that mean? So what is the meaning of this? This is true for x fixed, right? This is true for x fixed. Now I can move to the supremum. I can take the supremum because x is fixed, and now I can take the supremum on x, on that interval I. Then I obtain the norm. So now what I'm doing in this limit, I'm going back, right? So if I do that, if I take the norm, if I write the norm, what do we have? We have a uniform convergence, right? Because that's true for any, this x is fixed, so it's true for any x. Now, if I take the supremum on x, so this implies that because x is fixed, and this is true for a fixed x, so I just take the supremum, right? Taking the supremum, I can write here. The supremum on x there we have for epsilon, we can find such that n greater than n implies that, then I take the supremum, if I take the supremum, that it gives the norm, right? I will just write the norm directly because I'm taking the supremum, right? Instead of writing supremum equal to the infinity, now I just substitute f n, or I can swap the position, doesn't matter. I can say fnx minus f, it doesn't matter, right? Absolute value. So I can interchange the position the way I want. With this f, there's an equal to epsilon. So this, what is this? What is this definition? It's a convergence. It's a uniform convergence, right? For any positive epsilon, because epsilon is fixed, it's arbitrary, you can find, which is exactly the same rank n that we use for the Cauchy sequence, is the same n. We just take to the limit. So if we rewrite this, it's just, what does that mean? It means that this sequence, Fn, converges uniformly. Uniform means that with the infinity norm. Infinity norm is what we call the uniform norm, or it gives us the uniform convergence. And there's a result about uniform convergence. If I have a sequence of continuous function that converges uniformly towards a limit, that limit is also continuous, right? So I will just use that information here. So this statement, okay, let's call this 3. I'll just say equation 3 implies that this sequence of course of element of Ci converges uniformly to F, and therefore F is continuous. So this implies that F is continuous on the closed interval, and that's the N. That's what we wanted to prove. So it converges for that same norm, and the limit is there, and it ends the proof. Since it's for an arbitrary epsilon, it's for any epsilon, and that ends the proof. Okay, so all these steps, of course, you see it's short, but I had to detail everything for you to understand. Okay, I use the result of the uniform convergence, but you can still prove, you use the epsilon delta definition of continuous function. You can still do the same thing. So you can use this, this result, this one. You can use this result to show that from here, you have continuity, right? But it's even in the notes. If you, I did that in the note. On page 26, the last few lines uses that. Uniform convergence is a straightforward result when you know that result. Otherwise, you have to use the epsilon delta definition of continuity, but everything's already here. You rewrite properly, and you show the continuity of the function f. Right? You use that definition. You take a point x, you fix a point on the interval I, and you show that f is continuous at that point. You use the definition. And all that was written here will help you. Because the purpose will be to find what? The purpose will be to find the n. Because for epsilon, you are looking for n such that when sorry. You are not looking for either, you are looking for delta, because use n's for the convergence. If you write the epsilon delta, say epsilon delta. So for a fixed epsilon, we want to find delta such that for any, let's say, if you want to show that it's continuous at x0, you fix it x0, you put sub-0, so as not to get confused with f of x. So we want to show that we fix x0 in I, we want to show that f is continuous at x0. Because x0 is arbitrary, it will be continuous at any x0 in I, so throughout the interval I. So for epsilon positive fixed, you want to find delta positive such that for any x in the neighborhood of x0, that is, neighborhood of x0 means that x minus x0 in absolute value is less than delta. So you want to find that ball center at x0 of radius delta. So you will look for the radius delta such that once I am there in that neighborhood, it will imply that absolute value of f of x minus f of x0 is less than epsilon. That's the epsilon delta definition of a continuous function. And it is given there. It is there in the note. And for that, you'll be using this limit, right? You'll be using this limit, this one, to do that. Right. It's in the note, so I will not go through that. Just read it. Make sure you understand step by step and very well. Okay, now the next thing, you see, if you recall what we said somewhere about completeness, about equivalent norms, right? We saw that in Rn, all norms are equivalent. So if I want to prove continuity or convergence or whatsoever, I just choose one of the norms. But with infinite dimensional spaces, something can be true for a given norm and not true for another norm, because norms are not equivalent. So you have to be careful of which norm you select. Now, we have just shown that Ci with the infinity norm is complete. But it doesn't mean it will be complete for any other norm. But in Rn, if it's complete for a given norm, it will be complete for any other norm because all the norms are equivalent. But here, we will see another example. If we change this norm now, instead of taking the infinity norm, if we take, for instance, the one norm, we will see that it's no longer continuous, right? So that's what we are going to do. We are going to, instead of taking the interval AB, we are going to take the interval 0, 1, right, to make things more precise or more clear. So that's the next thing we are going to do. We are going to prove that is one star, this one, example star, now double star. So this is like first example, second example. Let me put a circle here around. Okay, now we need a second example. Okay. So now this is another example. Good. So now we are taking the same set of continuous functions. Now we are using the closed interval 0, 1. 0, 1 with the one norm. Is not a Banach space. It's not a Banach space. In general, to show that something is not a Banach space, you just select or you construct a sequence That would be a Cauchy sequence, but that does not converge. It's enough. That is you choose a counter example. Counter example. So we need to construct a sequence that is, we need to construct a Cauchy sequence that does not converge. And in our case, we can construct a Cauchy sequence that will not be continuous on the, over the closed interval. Because remember that the limit has to be an element of space. So if I find a Cauchy sequence that converges to a function that's not continuous at a single point, it's enough to stop there. Right? Because it might converge, right? But the limit has to be in the space. And for the limit to be in the space means that it has to be continuous over the closed interval. Any point there in the closed interval, the limit has to be continuous there. But if you can find a single point there where it is not continuous, I'm done. Okay, so we already have a sequence, right? We construct a sequence. So what I'm going to do, the main feature of this will be to give you like a graphical representation. So consider the following sequence. So consider the following sequence, Hn, of subset of Ci. In fact, it's a subset of C01 defined by H, right? Hnx. Okay, so you would take the function to be 0, right, for x between 0 and 1/2, right? And then it will be n into x minus 1/2. Right, yeah, like this for x between 1/2 and 1/2 plus 1 by n. One by n, and then the 1 right from here, 1 less than or equal to 1. So we are in the interval 0, 1. So we take that interval 0, 1, we break into 3 sub-intervals. Where it's 0, where it's 1. So we have 0 here, 1 there, and in between we have a straight line. Because you can see that this is a straight line. See, it's linear in x, right? So we have something like this. So because from here to 1, from 1/2 plus 1 by n, you will increase linearly to 1. Now you see that when n will go towards infinity, 1 by n will go to 0. So 1/2 plus 1 by n will go towards half, like this. So we have a step function. Yeah, step function. So it will be something like this. I squeeze it to the left because I wanted space here to try to depict what it looks like so that you have a good idea of what is going on here. All right. Very important what we are doing. So this is our axis. Okay. So this is 0. I will take 1 maybe somewhere here. This is 1. Oh, you can take 1 here. So 1/2 is somewhere here in the middle. This is 1/2. So now a 1/2 plus is very small, right? This is too small because 1 by n, depending on what n is. N cannot be 1 because if n is 1, wait. Yeah, n cannot be 1 because if n is 1, we already have 1.5, which cannot. Okay, what is this? Yeah, it cannot be 1. Eh? Yeah, it cannot be 1. Okay, that cannot be 1. It cannot be 1 because if it's 1, it cannot be less than 1, right? Take a sequence where n is greater than 1. You can start from 2, 3, and whatsoever. So you see that when this n becomes very large, then you get close. So it is somewhere here, it's too close, but I will just maximize, or I mean amplify, magnify. I will magnify that space so that it will look right. So this is 1 by n. This is 1/2 plus 1 by n. Okay, let me do this. Let me make this red or reddish. Good. And this is 1/2 plus 1 by n. Okay, so that is it. So we are here from here. So I will use which color now for the graph? Green, or red. Okay, red will be better. So here from 0 to x by that. Oh no. Okay, let me take something that is a bit, which is big. So here we have this. Well, we are here. We have this. Right. All right, and then. Okay, so our 1, we will take 1 to be here. Right, we will take 1. Okay, so this is 1. So this is 1. Okay, the problem that I have here is this software, because yeah, I have a problem, a lot of problems with the software, because there's another version which is not this one, where I can easily. Okay, let's say that this is on here. Now the problem that I have, but it will be easy. I will solve it easily, but I could have avoided it if I could use this straight line as a dotted line or dashed line. I have that problem with this software. But the other one on the other laptop, I can do that directly and have my dashed line. But here, if I want to do the same thing, what I will have to do, let me do it quickly. Ooh, now there's a problem because I can't see. Okay, let me see. Okay, it's here. Now move somewhere. Okay, it's already here. And then take some time. Okay. Yeah, let us leave it like that. At least we can see that this is a dashed line. Okay, so now we continue. We continue with our red line. Because we know that there will be one from here to there. Assume that it goes like this, and then we have one. Okay, now in between, we have this. Wait, yeah, from one to that point. But you see that this point is moving. This point is moving 1/2, 1/2 plus 1 by n. Right. So this dashed line can move and coincide with this red one. And in that case, the red line will become absolutely vertical and the two will coincide. And that will be at 1/2. So what I'm trying to say is that this, right, as n will go to infinity, you have this, something like this. You have that. So that's exactly the problem that I was saying I'm having. But anyway, let me try. I would just try. I would just try. I will try to see if I can draw something. It's not that. Okay, let me see if what I want to do will be successful. Now, if I select this, I select this. I do the copy and paste. Then I take this here. And then I do this. Oh my God. Paste. I don't know why this, when I try to change the color, now it becomes okay, that's not a problem. It's really unfortunate. Okay, if I do this, anyway, this is better. But unfortunately, it's taking time. Software. Okay, so it will be somewhere here. Okay, so this will be the limit. This red, the shaded one, this one. So this will be the limit. And I will call this limit h. This is h of x. In fact, the function itself is h, right? Okay, so now this one is hn. hn. Now it will converge towards this. All right, now if you look at the graph, you will see that each function hs is continuous. Graphically, you can see, anyway, you can even see from here. First of all, it is constant here and there, and here you have a linear function, and they are connected. How do you look at the continuity? We just look at the point here at 1/2 and here. Just make sure that the limit on the right, on the left, of this point at 1/2, that this limit when x goes to 1/2 is equal to the value of the function here. So when x goes to 1/2, it will be 0. So it gives this value. So there's connection. Similarly here, at this point, 1/2 plus 1 by n, if you take the limit here, when x goes towards this point, it will give you 1. Right? That's the limit. So it means that they are connected. So you can move from one end to the other one, right, without lifting the pen. So that's continuity. So it's continuous. So I would just state, I will write it here. For any n, of course, in our sequence, we don't allow n to be 1, right? For this, what I mentioned here, you have a sequence, n start from 2, 3, 4. You cannot take the value 1 because of this. This point will not be in the interval. Hn is continuous. On in that interval. Because we say we consider it there, but the way we consider, we can say something and consider another thing that does not satisfy the condition. So you can see that it's well defined. Right? We check that it's actually continuous, but which is the case, right? Everything is clear. Now, is this a Cauchy sequence? That's the next question. Because we say that we are making this, we are proving by counterexample. Let's take a counterexample. Is this a Cauchy sequence? That's the next thing we need to look at. Right. We will say that it is a Cauchy sequence with respect to one norm, and we are going to prove it. So the second information is that Hn is a Cauchy sequence. Cauchy sequence. It's a Cauchy sequence of element of that with respect to one norm. So with respect to the one norm. Now, how do we prove it? How do we prove that something like this is a Cauchy sequence? For a given epsilon, for a fixed epsilon, I can find a rank such that for m and n greater than the rank, the one norm of hn minus hn is less than epsilon. So that is how we prove it. Let's do that. So we are going to construct. Not construct. We are going to select 2h, hm and hn, but we will write m in terms of n, right? Because of this, we don't want to have m and n. The m should be in terms of n, so that we just deal with a single something, with single n, right? So for that, let's do this. So we will write let and it's possible one. Let m n in for two natural numbers, not one. That's assume. Wait. Okay, I can take n greater than n. So if it's greater than n, because they are all integers, it means that m can be written as m plus a certain p. Let's say, for instance, I take 10 and 200. I can always write n, which is 200, as 10 plus 190. And that 190 is my p. So once I have two integers, one is greater than the other one, I can always write the greater one than the lower one plus p. Let me take another example. If I take 7 and 11, m is 7 and n is 11. So if I write 11 in terms of 7, I will say it's 7 plus 4. So my p is 4. So you can do that for any arbitrary number. So now you see that of course, p is there, and that is it. So okay, now what will I do? Then I write this norm. I can write the norm, the one norm of m minus n, one norm, as the one norm h m minus h m plus p. Right. Now, the good thing here is that since we are dealing with positive function, you can see that these functions are all positive, right? They're there. Right. Now, if I take the difference of these two, I can write this. I can write this because I'm taking the difference of the two. The difference of the two, in fact, that norm is in fact is the area between the difference, right? That difference, I take hm minus hn. I'll have something like this. It will not be easy to see it from here, but let me copy this. If I copy this, good. But unfortunately, I can't magnify this. But it's not a problem. But the good thing here is that if I take, okay, I will change this into m. Right, 1 plus this for the interval. This is for hm. Now, if I take H1, if I want for the other one, HM plus P, it will be somewhere here. Why? Because HM plus P this one will be greater. That is, this one will be less than. Because this is greater than that. Then if I take the reciprocal, it will be lesser. So it will be somewhere here. Somewhere here. So let me add that one here. Now, if I add that one here, we'll have something here like this, something like this, right? Like that, like this, and then that line, this one, it will still coincide here, and then from here, it will go there. So let me use that one. And then it will go there, right? And then it will continue like this, of course, till there. But I don't want to cover that, right? I don't want to cover, I'll just do this. For you to see that here, this will be HM plus P, and this point here will be 1 by N plus 1 by M plus P. So that point will be here. I could have enlarged it, but it will take time, and particularly due to the fact that my software does not have those things of. Let us not waste too much time. Okay, let me see if I can enlarge. Let me see for that enlargement. But if you understand already what I'm explaining is okay. But let me see if I can try to enlarge this. Let me see. I don't know what it will look like, but let me see. Oh, wait. Vertical space. Oh no. Vertical space. I don't know. Oh. Anyway, I don't know. I don't know how to do that. Anyway, it doesn't give us side by side. Oh. Okay. Okay, now, if I take the difference, you agree with me that if I subtract this, this from that, or that from, if I take the difference, this will be 0, this will be 0. But now here, I will take this one minus that. And that will just be the area in between the two. So that will be this line, this part. It will give us this area. I don't really know how it will look like, but let me see. let me try. Okay, it will give us this area between the two. Over here. This area between the two. So that's the area, that area. And what is that area? It's a triangle. You can move it the way you want. It's a triangle. It gives us a triangle. See? Regardless of the position, it's a triangle. It's a triangle. Because here, this line will always be straight. It will be horizontal. This is horizontal. That point is there. 1/2 is fixed for both. And then you have that. And then you have, it's a triangle. Okay, now let us write let us write that portion. That portion. So now this is equal to what? We know already that is this area in between. So what is it? So that will reduce to the integral from one half wait, let me see that properly. Okay, so this first part, this one and this one will cancel out. They will just disappear. Now we'll be here. We'll be here in this interval. This one. Oh, yeah. Okay, yeah, it's much better. Okay, so we have this triangle. We have this triangle from here to there. The area below. What was I talking? Okay, so the area, I think maybe what I wrote there was not correct. So this integral, this first one, this integral, will be the area below the curve. So it will take from 1/2 up to this. So it will be this entire area from here. It will be all this area like this. All that area. Now for the next one, it will be the area like this till there. Now, if I take the difference, because this one will be higher, yeah, it's exactly what I shaded there. Because if I take this interval like this, it will be everything here and that one. Now, if I take the difference, it will remove this part, and we'll be left with this interval inside. Yeah, correct. What I wrote there is correct. Eh? All right. Now, because I'm subtracting, this portion is still there. Can I remove this portion? My question, where is it? My question is, am I supposed to keep this? Yeah, we have this line like this. Am I supposed to keep this part? This one before the line. Am I supposed to keep that? And keep this one only. Okay, so let us write in detail, right? Okay, so let's write that integral in detail. So the integral is this. Yes, that will be the case because of the way we selected this n. We wrote that n in terms of m, right? If you write that in terms of m, then we will only be left with this sub-interval. So anyway, let's write that. Let's write that in details. Let's write everything. Let's write everything. Okay, so now we know that we are here. We will be only in this interval. Now, when we will take the difference, when we substitute here, m and n here, and take the difference over this interval, we will end up with this interval. We end up with the interval, the smaller interval, which is this one, 1/2 plus 1 by m plus p. So that one is smaller, m plus p, and then 1 by n plus 1 by m, right? We end up with this one, p into x minus 1/2. x minus 1 half dx. This is what we end up with. But let's see that. I'm saying it because this is in terms of that. So when we substitute, this is what we will end up with. So let us write this definition with the one norm. So what is our one norm? It's important to know this. So our one norm, of course, we have a continuous function here. From 0 to 1, right, is this one, absolute value of f of x dx. This is what our one norm is. Now, if you write because C is a vector space. So if I take the difference of 2, it will give us a single function, right? Because remember, in a vector space, if I add 2, it's still a single function in that. Now, if I take the difference, we know already that if I take the difference, and I integrate, right? Let us do that. Hm minus Hn will be this integral from 0 to 1, the absolute value. Anyway, Mn doesn't matter when I take the difference, like that, dx. That's what I have. Okay, now, I will split this interval into integral from 0 to 1/2, from 1/2 to this, and from this to that, and from this to that. I can split and substitute the corresponding. Obviously, we assume that n is greater, right? N is greater than m. So if that is the case, this interval, let me call this h m n of x. So this will give us the integral from 0 to 1/2 h m comma n of x, of course in absolute value, dx plus the integral from 1/2 to the next, which is 1/2 plus 1 by n, absolute value h and m or mn, doesn't matter, that order is not important, dx, plus now the integral from this point, 1 by 2 plus 1 by n to this next point, plus 1 by m, right? Absolute value h n comma m x, that is in absolute value, plus the last interval from this 1 by 2 plus 1 by m to 1. That function h n comma m of x dx. So if you split our interval into the 1, 2, 3, 4 portion, 1, 2, 3, 4 portion. Okay, but we know that from 0 to 1/2, they are all 0. So this will go to 0. The first one, this one will go to 0. And from okay, it will be 1. Once we exceed this, it becomes 1. Right. So once we exceed one of these two, it becomes 1. So meaning that once I exceed, so here, when I exceed this, it becomes 1. So it is 1 here. So this also will go to 0. Right? Because from here to there is 0. Is 1, sorry. When I exceed this ratio, once I exceed the ratio, it becomes 1. So this is 0 and this is 0. Now, we are here. From 1/2 to this, from 1/2 to this point, I'm here. From 1/2 to this point, I'm a linear function. Right? And also from here, in between the ratios, that is from this point to this point, that is between these two, between the two here, you can see that it's still have a straight line. So it's linear. And it's linear here, it's linear there. So if you combine these two linear, it's a linear function. Similarly, from here to there is still a linear function. I have this linear part, I have that linear part. Roughly from here to there is linear. I have a linear function. Okay. So where does it become 1? It becomes 1 from here. From here, this 1 is 1, right? The top part, once I reach the top here, it becomes 1. But even if I take 1 and I add to a linear function, it's still a linear function. So there we have linear function. So now let us look at how to write it. So this becomes this is equal to this integral from 1/2 to 1/2 plus 1 by n. Okay. Now for hn, for hnx, it is this, hnx. So from hnx, it is n into x minus 1/2 here. Now, what about the other one? hm. Now, for hm, obviously, for hm, this one, hm. So we are in between 1/2, and this is also linear, right? It's also linear. So that will be plus or minus m, same thing, dx. But now this m is in terms of that n. That's the difference. This m, no, that is n. Is n. N, we say that n is m plus p. Now, if I take this substitute there, you see that this m and this m will cancel out because you have plus m here, we have negative. So what will be left will be the p, this p, times this coefficient. That's what we will get there. So it gives us p. But I said that something was 1. Oh, well, we are in the interval 1, 2 here, 2 here. 1/2. It's linear. Yeah, it's linear. It is after that 1 will become 1. Okay, so when we cross that, okay. So we have this. So we can substitute our p here. So this is p into x minus 1/2 dx in absolute value, of course. But it's already positive, right? P is positive. X is, you can see here, is greater than 1/2. So all this positive, I can remove the absolute value. So that is for this first term. Now, plus, now we are in this second interval, plus. Now, from 1/2 plus 1/n to 1/2 plus 1/m, even though this n is m plus p. Yeah? We will take that into account. Okay, now from this interval, 1 will be 1. If you look at here, so once I exceed this value, 1/n, this is n, because n is what we wrote, m plus p. So this is n, we are here. When I exceed this function hn is already 1. So it will be 1. So 1 minus this. So this is 1. So we have 1 minus this part. So you have 1 for hn. So this will be absolute value of 1 minus 1 minus, so this one becomes 1 minus hm. And hm is still linear, right? So that would be m into x minus 1/2, like this, dx. I hope what I'm saying is correct. Yeah, it should be. So this is what we have. Ends, and now from here to there, everything is 1. That is, this one is still here. It continues, and for the other, both are now 1, 1, 1. So that will cancel out and become 0. I think that's what I see. Huh? Am I wrong or am I right in this statement? And this is still a linear function. And how can we write this? Obviously, this m with m, because everything should be in terms of m. We wrote everything in terms of m. Yeah, everything is in terms of m. Okay, so what is this? Now, if I expand this, this expression, what is it? So this is plus m there. So if I expand this expression, this is 1 minus mx plus m by 2. Right, we can put this together. It's linear. But we say that m cannot be 1 for the reason that we already mentioned. So m starts from 2. Right. So what is the purpose of doing all this? Anyway, it's just to show that it's anyway, absolutely, we saw that it's positive because everything is here above. So it's positive. So this is positive. This is positive. Because we are here. So it is positive. I just want to see, because proceeding this way, there's something, it doesn't give the expected result, but there's something, I think I might have gone wrong somewhere, but I want to make sure that's what I'm. Okay, but what is obvious is that from what is here, if this one, the one that is below, if m becomes more and more small, these two would coincide. That's why we can see graphically. This yellow, if both m and n, I mean, if we fix m and take p to go to infinity, we can see that this two will be converging towards this line. So this space, this yellow space will go to 0. This area will go to 0. And that's what we need to show. You can see it from here. For m becoming very large, we all saw here that when m becomes large, this will go towards 1/2. This also will be going towards 1/2. and this yellow band would disappear. And that yellow band is this integral. So that integral will convert to 0. And that's what we need to prove here. So this idea of 1 because I still have in my computation, there's still a problem here with that interval, the manipulation. Because the separation here is correct, no? Because the one that will be problematic is mainly this one, where I still have 1/2 here. But when I did that previously, it gives me an interval that depends only on n, but I still have that. And that's what I would need to find out, right? But for now, I will keep this, and because of the time constraint, now I will quickly conclude here. This limit has to go to 0. You can see it graphically, but I will try to check properly because when I designed this note a few years ago, this is exactly what I got, what you see on the note. But when I try to do it now, but I still have that interval, this 1/2 appearing. One half is still appearing. Well, 1/2 is still appearing. 1/2 is still appearing. One half. Mm-hmm. Okay, now for the second one, I have that straight line. Okay, so regardless of the situation here, even if we keep this anyhow, we have to show that this goes to 0. We need to show that this one converges to 0. Right. When now we take the limit when m goes to infinity. Because p is fixed, right? We fix p and we take m to infinity. Right? So we fix this. So if you replace it here, this will be m plus p. P is fixed. So you have the m here, we take m to infinity. So please have a look at this. For next time, let me write it down. I'll have to look at this and I'll communicate on that. So on this note, we stop here. Thank you for your kind attention. It's getting late. God bless you and see you next time. Bye-bye.